As a civil engineer, I think this is the very basic job to design a beam. So in this video, we'll learn how to design a beam as per Indian standard, and also we will learn how to use SP16 for designing a beam. Okay, so welcome to my channel. If you are a civil engineer, please subscribe this channel to get videos on analysis, design and construction. So very first, assume this is the frame. Okay, and we have to design this beam. So for designing any beam or any structural member, first we have to calculate how much load is coming on that structural member. So here we will assume that the UDL or uniformly distributed load which is coming on this beam is equal, and the value of this UDL is 100 kilonewton per meter. Now for designing your beam, you have to calculate two things. One is the moment which is coming to this support and to the midspan of this beam, and another thing is, that is the shear force which is coming to this support. Well, if you don't know how to use any software, or if you don't have any software to analysis this frame or the structure, you can use the Indian standard, where it has been mentioned that if you fulfill certain criteria, you can use this coefficient to calculate the moment which is coming to your support and also to the span. Now what are the criteria to use this table or to use this coefficient which is given in table 12 of IS456 2000? Well, the first criteria is that the UDL or uniformly distributed load over 3 or more span. Here there are 3 span, and also this UDL should be almost uniform. Okay, and what is the next thing? The span. That means the span of this beam. Here the first span is 5 meter, second one is 4.5 meter, and last one is 5 meter. So the span should not differ by more than 15% of the longest. So what is the longest span here? It is 5 meters. So what is the 15% of 5 meter? Let's calculate. So 15% means 0.15 into 5. It's coming as 0.75. Okay, so 5 minus, if you calculate 5 minus 0.75, it will give you 4.25. So if this span is up to 4.25, not less than that, if it is 4 meter, in that case we cannot use this table, but here it is 4.5 meter, so it is within 15% limit. So now calculate the bending moment and shear force which is coming to this beam. So first you have to calculate two bending moment. You know that in concrete structure, this support can be treated as fixed support, and for a fixed or continuous beam there are two moments. At support there is hogging moment, and at span it is sagging moment. Okay, and you know that for hogging moment you have to provide reinforcement at the top of the beam, and for sagging moment you have to provide reinforcement at the bottom of the beam. Okay, so now look at the table. There are two moments, span moment, just I have said you, and another is support moment. And for span moment there are two tables. What are they? First one is for near middle of end span. This is the end span, near middle of the end span, and this one is for at the middle of interior span. Now in this video we will design this beam or the interior beam. Okay, so we have to consider this one. Now for this there are two values for finding the span moment or middle moment or the sagging moment at the midspan. What are they? First one is dead load plus live load which is fixed, and second one is for only live load which is not fixed. Okay, we will assume that our design load or this UDL load is coming from this dead load plus live load combination. Okay, so we have to take this value. What is this? Plus 1 by 16, and for support moment we have to take this one. Here it is mentioned that at other interior support this is minus 1 by 12, and this value is again for end support. We are considering the interior one, so we will not take this one, we will take this one. This is mentioned as minus 1 by 12. Why minus? Because at support there is hogging moment. That's why this minus sign has been indicated. So how we have to use these values, or 1 by 16 and minus 1 by 12? Well, you can see here that at note it is mentioned for obtaining the bending moment, this coefficient, that means this 1 by 16 or minus 1 by 12, this coefficient shall be multiplied by total design load and effective span. So find total design load. If you know the span and if you know the design UDL load, you can calculate the total load just multiplying them. That means 4.5 into 100, which is coming as 450. So you have calculated the total design load. Now what is the effective span? Let's assume 4.5 meter. Okay, so you have got these two values, effective span and total design load. Now using this coefficient, you can simply find the moment which is coming at the support and also at the mid span. So at the support, the negative moment or hogging moment is coming. What is the value? Simply multiply by minus 1 by 12. So I multiplied it with minus 1 by 12 into this total load into the span or the effective span. This is coming as 168. Okay, simply I have calculated the span moment also. Now I am not talking anything about shear force or how to design shear force. I will make another videos for designing a beam for particular shear force. At that time I will discuss how I am getting this shear force by using the table. Okay, so for now we have calculated our moment. Now it's time to design our beam, the very basic job of any structural engineer or civil engineer or whatever you call yourself. Okay, so let's start it. What is your moment? This is, just ignore this minus sign. This minus sign only indicate that the reinforcement you have to provide at the top of the beam, and it is only valid for the support where the hogging moment is coming. So don't be confused with the minus sign. Okay, here just take it as 168.8 kilonewton meter, for which we have to find two things. One is the dimension of the beam, that means the depth and width, and the reinforcement or the steel which you required. Okay, so the very first step is you have to select the depth of the beam. Just I have mentioned it. What is the depth? Well, if you don't know what is depth and what is width, for you this is okay. If this is your beam, so this is the depth. Okay, this one is the width and this one is the depth, and your reinforcement lies somewhere here at the bottom, or for support here at the top. Okay, now it is clear to you what is a beam looks like, what is its depth and what is its width, and where the reinforcement actually lies. So how do you have to calculate this depth? You cannot assume it arbitrarily. There are some basic values. Okay, basic values from which you have to calculate the or assume the depth of the beam. What are they? Well, as per IS456 2000, it is mentioned that if your span is 1 and effective depth is say D. Okay, so the value of 1 divided by D is 7 for which type of beam? Cantilever, 20 for simply supported beam, and 26 for continuous beam. Well, in our case, what is the nature of this beam? Obviously this is cantilever beam. No, this is not cantilever beam. Then yes, it is simply supported beam. No, again you are wrong. This is not simply supported beam. This is continuous beam. Okay, this is continuous beam. Well, if you don't know what is cantilever, what is simply supported, or what is your continuous beam, then let me know in the comment box. Obviously I will make videos on that. So for our case, this is continuous beam. Okay, and for continuous beam, what is the basic value for this particular span by depth ratio? This is 26. That means, let's say the span of your beam is 5 meter or 5000 mm. Okay, so what should be the depth? Obviously depth should be is equal to your 5000 divided by your 26, because your beam is continuous beam. So it is coming as 192. In our case, what is coming? The span is 4.5 meter. So effective depth is coming as 173. Now what is effective depth? Effective depth means if your, let me draw the reinforcement for your better understanding. So let's say this is the reinforcement lying here. Okay, so effective depth means the distance from this top fiber to the center of this reinforcement. Okay, so for total depth you have to add the half of the reinforcement plus the stirrup diameter, the stirrup will be at the bottom of the reinforcement, and the clear cover. Okay, so normally the clear cover is 25 per beam, stirrup diameter is 10 mm, and let's assume your diameter of reinforcement will be 25 mm, so half of that is 12.5. so effective depth plus 12.5 plus stirrup diameter plus clear cover, it is coming as 220 mm. So this should be the depth of your beam for satisfying this clause. And why this clause is introduced? To limit the vertical deflection. This is not from the moment carrying point of view. So you have got a depth. Okay, so for right now just assume the 220 mm is the depth, and assume another width. You can assume depth, you can assume any width. For now just assume 300 mm. Okay, so now we have to calculate whether this depth is sufficient, and if this depth is sufficient, then for this depth and this width, what should be the amount of reinforcement to carry the moment of values 168.8 kilonewton meter. Okay, so now we are going to check whether this depth is sufficient or not, and also if sufficient, how much reinforcement is required. Okay, so for that you have to put, or you have to assume what type of concrete and what type of steel you are going to use. Well, M25 of concrete is a very common concrete. Well, we will assume that you are going to use M25 concrete, and also we will assume that Fe500, this is very common in market now. Fe500 steel you are going to use for construction of this beam. Now based on this input, especially based on the grade of steel, there are some XU by D value. What is XU by D? Well, jump into the IS456 2007. Now every term we will discuss based on this code. Okay, code is saying that XU by D, or the depth of neutral axis. X is the depth of neutral axis, which is somewhere here. So depth of neutral axis divided by D, or effective depth. You have already learned what is effective depth. So for limiting condition, XU by D is 0.46 if your steel is of Fe500. That is why I have taken 0.46. Okay, as we are using IS456 2000, here the design is totally based on limit condition or limit state. Okay, we are not designing as per working stress method, we are designing based on limit state method. Okay, already got the width, grade of concrete, grade of steel, the limiting value of XU by D. You have learned what is XU by D. So now calculate what is the depth required. You have already got a depth based on deflection criteria. Now based on moment criteria, you have to check whether this depth is sufficient or not. Now how you will get the depth, required depth for particular amount of moment, and with the given weight, grade of steel, grade of concrete. Okay, well, as for 456 2000, you will get at the annexure these formulas. Okay, the moment carrying capacity of a beam is given by this formula with some condition. Take this clause, or clause C. What is said? It is being said that if this XU by D value is equal to the limit value, or 0.46, then the moment of resistance of the section is given by this formula. What is the implication of this formula? The moment of resistance of the section is governed by the concrete, the yielding or crashing of the concrete. This is the implication of this formula. For finding out the depth of the section required for particular moment, we will assume this formula, or we will assume that our section is in limiting condition or at limit value. Okay, so XU by D is given by limit value, that is 0.46. It comes from grade of steel. Again, XU by D, it is known to you. B, or the width of the section, you have assumed as 300. FCK, or the grade of steel, that is 25, is known to you, and moment for which you are designing the section is also known to you. So if each of every parameter of this equation is known to you, the unknown thing is D. Okay, or the effective depth of the section. So from this equation you can find the effective depth which is required for this moment. In our case this is 168.8 kilonewton meter. Well, let's find the depth. Just applying this formula, we have got our depth is required, effective depth or small d is required as 410.4 mm. Just applying this formula or this formula. Okay, here everything is known, only d is unknown. So you can find small d. So from that again calculate the required d, because you have calculated small d or effective d or the distance between the topmost fiber to the center of the bar. Then you have to add how much? Half of the diameter of the bar, diameter of the stirrup and clear cover of the beam. So half of the diameter of bar is 12.5, stirrup diameter 10, clear cover is 25. We are getting how much? We are getting as 457 mm. Well, this is not possible to construct a beam with such a depth. Let's round it off in multiply of 50. So we are getting the depth as 500 mm. Obviously the effective depth also changed. How? Well, clear cover is 25, it should be subtracted, 10 mm stirrup diameter should be subtracted and 25 mm main bar we are providing. So half of that diameter should be subtracted. Now we are getting effective depth as this much. So from this equation you got a very important thing, that is the depth of the section. Previously you have assumed the depth of the beam as 300 mm. Now you have calculated the depth of the beam as 500 mm. So you have almost completed half of the design part. The remaining part is only you have to calculate how much this reinforcement or you can say the steel bar is needed for this section. Okay, let's calculate that. Well, our assumption for calculating the depth of the beam was that the section is in limit value. Okay, so what does it mean by limit value? Limiting value means that the compression force and tensile force within the section is same, and from that you can say that the value of xu by d at limit condition should be this much. The ratio of the neutral axis to the effective depth should be this much. Well, from this equation we will calculate which one? Area of steel which is required. Okay, so next step is to calculate the area of steel, assuming that our section is in limit condition and the value of xu by d is 0.46, which is valid only for in limit condition. Okay, so use this. You know the value of xu by d is 0.46. You know fy as 500, fck as 25, b as the 300 or the width, and the d which you have just calculated as 500. No, 500 is the total depth. You have to calculate the effective depth, that is 452.5 mm. So from here we can calculate the area of steel which is required for our design. So from this formula I have calculated here, and the area of steel is coming as how much? 1291 square mm. Start with 16 mm bar. Let's provide 4 numbers 16 mm bar. Here it is only 803 mm square. Just increase it to 20 mm dia. In this case it is 1256. Well, increase the number, let's say it's 5. So in this case it is 1570, which is more than the required. That means you may think, well, it is okay because the required steel is 1291 mm square. I am providing more than that. Well, here you have to check certain thing. What is that? This is the formula which you have used for finding the area of steel. Put the value of xu by d as 0.46. What is this? This is valid only for the limit condition, and for limit condition you have applied this formula to find out the depth. So everything is based on the assumption that the section is in limit state. So the section is in limit state or not after providing this steel. How? If this value or xu by d value by using this formula is coming as 0.46, then it is okay, it is in limit state. And if it is not, then we have to think otherwise? Well, first check it. So here I have checked the value of XU by D. This is coming as 0.559. Our limiting value was 0.46, but here it is coming as 0.559, much more than that. So what is code saying? Code is saying if the value of XU by D is greater than the limiting value, or the 0.46 in our case, then the section should be redesigned. That's why here it is coming as redesign. Well, I am using the Excel sheet for making this video, that's why everything here is in foreground condition. This is the XU by D and everything is depend on this value. So we have assumed that it is in limit condition. So here these values should come as 0.46, but it has come as 0.559. Why? Here at the denominator there is AST, or area of steel. So when you have calculated AST, it has come as 1291 something, but you have provided more than that. Well, that's why the value of XU by D is more than the expected 0.46. So always you have to provide the steel here less than this value. In only that case the value of XU by D will be less than 0.46. If it is less than, then it is okay, but if it is more than that, you have to redesign the section. So greater than this value is not allowed at all. Simply reduce one bar, make it 4. In that case, yes, this is less than. If the value of the provided steel is less than the required one, in that case there is a problem. What is code saying? Code is saying if this value is less than the limiting value, in that case the moment of resistance of the section should be calculated based on the yielding of steel. Well, during the find of the depth of the section, we assumed that the moment of resistance of the section is governed by the yield or crashing of the concrete. But here the code is saying if this value is less than the limiting value, which is our case. The limiting value is 0.46, but it is coming as 0.447. That means less than the limiting value. The code is saying that you have to check your moment carrying capacity of the section based on yielding of steel. Okay, so we have to check again by using this formula. Everything is known. Fy is known 500. AST just you have provided as 1256. Effective depth, you know, this is the effective depth, 452.5. AST area of steel, you know, Fy is 500, B is 300, effective depth is 452.5 and FCK is 25. From that you calculate the moment carrying capacity of the section, and this is coming as 201.5 kN and our requirement was 168.8. Well, that means the section is okay. So what is the finding? The finding is that first we assume the section is in limit condition. Based on that we find the depth of the section. Okay, then from this formula we find the area of steel and we check whether the section is in limit state or not. We provide less steel to avoid the redesign of the section, and for that this XU by D value is less than the limiting value, and we have to check the moment carrying capacity based on the formula which is governed by yield of steel. Okay, so this is all about designing the beam based on IS456 2000, and you can say based on limit state method. You can check this steel requirement or the section size as for SP16. Okay, here to use SP16, which is required, you need to know what is the grade of the steel. In our case this is 500, and what is the grade of FCK or concrete, this is 25. So using this table you can find what is the percentage of steel required. Just calculate mu by bd square. Mu, you know, mu is 168, b is the 300, d is the 457.5. so you calculate mu by bd square. This is coming as 2.75. Go to 2.75. Where is 2.75? Yes, this is here, 2.75. So based on 2.75 and for Fe500, the percentage of steel required is 0.744.